In 1879, the Denver and Rio Grande Railway hung a railroad bridge from iron cables across the Royal Gorge of the Arkansas River in Colorado. The canyon walls at the bridge site stood 30 feet apart and 1,053 feet deep. Chief Engineer Charles Shaler Smith designed an A-frame iron truss anchored directly into the granite walls. The bridge opened to traffic in 6 months. It is still in use today. 1,053 feet deep, 30 feet wide at the bridge site. No foundation possible because the canyon walls drop almost vertically into the Arkansas River below. No false work possible because there was no place to put it. The engineering problem the Denver and Rio Grande Railway faced in 1879 was unique in American railroad construction up to that date. They needed to run a narrow-gauge railroad through the Royal Gorge of the Arkansas River in Colorado. The route was strategic. It was the only practical way to bring rail service from Pueblo, Colorado, west to the silver mines of Leadville. The railroad that owned the route would dominate Colorado mining freight for a generation. The railroad that did not own the route would lose Colorado entirely. 2 railroads claimed the route: the Denver and Rio Grande Railway and the Atchison, Topeka, and Santa Fe Railway. The conflict over who owned the canyon was called the Royal Gorge War. It involved armed standoffs at the canyon mouth, lawsuits in 3 federal courts, and ultimately a brokered truce by railroad financier Jay Gould in 1880. The Denver and Rio Grande emerged with the route, and then they had to build it. Building the route meant solving a problem nobody had solved before in American railroad history. At one specific bend in the canyon, the walls narrowed to 30 feet apart. The Arkansas River filled the entire floor of that gap. The granite walls rose almost vertically above the river. There was no shelf, there was no bench, there was nothing wide enough to run a railroad track on. To get through the canyon, the railroad either had to dig a tunnel through the canyon wall, which would have taken years and bankrupted the company, or it had to figure out some way to suspend a railroad bridge from the canyon walls themselves. Suspended, from the rock, without false work below, without a bridge pier in the river, just hanging from iron cables anchored directly into the granite. The man who solved the problem was Charles Shaler Smith. Smith was 42 years old in 1879. He had been born in Pittsburgh, Pennsylvania in 1836, the son of a Scotch-Irish immigrant family. He apprenticed under James Buchanan Eads on the Mississippi River salvage operations in the 1850s, then worked as a young engineer for the Union Army during the Civil War on military bridge construction for the Tennessee River campaigns. After the war, Smith partnered with Benjamin Latrobe Jr. at the Smith, Latrobe & Company engineering firm in Baltimore, focusing on bridge and tunnel work for Southern and Western railroads. The Smith firm designed bridges across the Tennessee River, the Cumberland River, the Yazoo River, and the lower Mississippi tributaries. By the early 1870s, Smith had moved west with the railroad expansion, eventually settling in Denver as the principal bridge engineer for the Denver and Rio Grande Railway under General William Jackson Palmer. He was not particularly famous in 1879, though he had a solid reputation in the Western engineering community. He had never designed a hanging bridge of this type. Nobody had. The Royal Gorge War that preceded the bridge construction deserves a brief technical summary because it determined who would even attempt the engineering. In 1878, both the Denver and Rio Grande Railway and the Atchison, Topeka, and Santa Fe Railway claimed the Royal Gorge Canyon route. The Santa Fe filed paperwork with the Bureau of Land Management in Washington, claiming the right-of-way. The Denver and Rio Grande filed competing paperwork. Construction crews from both railroads arrived at the canyon mouth in 1978 and began building competing rights-of-way, sometimes within 50 feet of each other. Local sheriffs deputized armed contingents from each railroad. Stone walls and earthen barricades appeared along the canyon. 3 minor armed standoffs occurred between Santa Fe and Denver and Rio Grande crews during the spring and summer of 1878, with several wounded but no fatalities. The dispute reached federal court in 1879. Judge Moses Hallett of the Colorado Federal District ruled in favor of the Denver and Rio Grande on the right-of-way. The Santa Fe appealed. The case went to the United States Supreme Court. Before the Supreme Court issued a ruling, the financier Jay Gould brokered a private settlement in February 1880. The Denver and Rio Grande received exclusive Royal Gorge access. The Santa Fe received exclusive Raton Pass access in southern Colorado, plus a cash payment of $1.4 million. The Royal Gorge War ended. The bridge construction could begin. The American hanging bridge tradition that would later produce the major suspension bridges of the late 19th century was just starting to develop. John Roebling had completed the Allegheny Suspension Bridge in 1860 and was working on the Brooklyn Bridge cable system in the 1870s. But those were full suspension bridges with their own piers and their own pre-stressed cable systems. What Smith needed was something different. He needed a structure that hung from cables anchored directly into a cliff face, with no piers, no foundation, and no false work. He needed an A-frame iron truss bridge suspended from rod cables, with the railroad track running on the suspended deck. Smith designed the bridge in 3 months, in the spring of 1879. The design called for a deck about 175 feet long, supported by iron rod cables that ran upward and outward at a 45-degree angle to anchor points drilled into the canyon walls above. The deck was an iron truss assembly. The truss consisted of cross-braced iron beams forming an A-frame shape when viewed from the side. The narrow-gauge railroad track sat on the truss deck. The deck was reinforced with iron rod tension members that prevented sag under loading. The cables were hand-forged wrought iron rods, 2 inches in diameter, made by the Phoenix Iron Company of Pennsylvania. The anchor points were custom iron sockets driven into pre-drilled holes in the granite, then grouted with a hydraulic cement compound that Smith had developed for canal lock work in the 1860s. If you appreciate the depth of these American industrial heritage stories and want to support more of them, join at the Boss tier for early access and members-only polls, or Final Boss for member shoutouts and members-only videos. Link is in the description below. Now we walk through what actually happened on the canyon floor when the construction crew arrived in June of 1879. The Phoenix Iron Company that supplied the iron rod cables for the Royal Gorge Hanging Bridge was based in Phoenixville, Pennsylvania. The Phoenix Works was one of the largest iron and steel fabricators in the United States in the 1870s, supplying iron components for bridges, railroad cars, locomotive boilers, and naval ironclad armor plates. The Phoenix process for wrought iron rod production used hammer forging, followed by rolling and tempering. Each cable rod for the Royal Gorge Bridge was approximately 2 inches in diameter, 15 to 20 feet long depending on the specific anchor location, and weighed roughly 80 pounds per linear foot. Phoenix Iron forged the rods to Smith specifications in their Pennsylvania works, then shipped them by rail to Pueblo, Colorado, where they were transferred to the Denver and Rio Grande narrow-gauge supply train. The total iron content of the bridge was approximately 40 tons, all of it manufactured by Phoenix Iron, all of it forged by hand hammer methods rather than by modern rolling mill or Bessemer converter steel processes. The wrought iron of 1879 had a tensile strength of approximately 50,000 pounds per square inch. Modern structural steel, by comparison, has a tensile strength of around 60,000 pounds per square inch. Smith designed the bridge with a safety factor of approximately 3, meaning the maximum design load was approximately 1/3 of the cable rupture point. That safety factor has proven adequate. The bridge has not failed in 146 years. The crew that built the bridge was about 20 men. The foreman was John Carroll, a Denver and Rio Grande veteran who had worked the standard tunnel and bridge sites of the 1870s. The team included masons, riggers, ironworkers, and laborers. They camped at the canyon entrance near present-day Cannon City, Colorado, and walked into the bridge site each morning along a rough trail above the river. The first work was to drill the anchor sockets into the canyon walls. The work parties suspended themselves on rope rigging from the canyon rim, drilled the anchor holes with hand drills and chisels, and set the iron anchor sockets in the holes with the hydraulic cement grout. Each anchor required about 3 days of work for a 4-man crew. The bridge needed 16 anchor points total, 8 on each canyon wall. The anchor work alone took about 4 months. While the anchor work proceeded, the bridge deck was fabricated at the Phoenix Iron Company Works in Pennsylvania. The components were shipped by rail to Pueblo, Colorado, then by mule wagon up the existing narrow gauge alignment to the canyon entrance. From the canyon entrance, the components were carried into the canyon on a temporary high-line cable system the crew had rigged on the canyon rim. The high line could lower components down to the bridge site on a hand-cranked winch. The deck assembly proceeded from the canyon walls outward toward the center line. Workers on rope rigging fitted each iron beam into its position and bolted it to the previous section. The work progressed about 10 feet per shift on a good day, with weather delays for high winds and snow squalls. The crew finished the deck assembly in November of 1879. The final tension testing of the cables was completed in December. The first scheduled narrow gauge train crossed the bridge in early 1880. Anyone who has seen the masonry on a 150-year-old bridge knows this. The Royal Gorge Hanging Bridge was not just engineering. It was a particular kind of engineering courage. Smith had no precedent for the design. He could not point to another bridge that had been built this way and proven its load capacity. He had to calculate the cable tension, the anchor stress, the deck stiffness, and the live load behavior entirely from first principles. He used the iron rod suspension precedents from the European Alps, where engineers in Switzerland and Italy had built smaller hanging footbridges over mountain gorges in the 1830s through 1850s. He used the cable engineering work of John Roebling on the Allegheny and the proposal documents for the Brooklyn Bridge. He used the early American iron truss bridge experience from the Mississippi River bridges of the 1870s. He synthesized all of it into one specific design for one specific site. And he was correct on all the major engineering decisions. The bridge held. The Denver and Rio Grande Railway ran scheduled narrow-gauge trains across the Royal Gorge Hanging Bridge from 1880 until the gauge conversion to standard gauge in 1906, then standard gauge trains until the line closed for through traffic in 1967. After the closure, the bridge sat idle for several years. The Denver and Rio Grande Western, the successor railroad, sold the right-of-way to the Canyon City and Royal Gorge Route Railroad operators in the 1970s. The Royal Gorge Route now runs scenic and excursion trains through the canyon, crossing the hanging bridge multiple times each day during the operating season. The bridge has not failed. The cables have not snapped. The anchors have not pulled out of the granite. The iron has held. If you are new here and enjoying this kind of historical depth, subscribe so you do not miss the next video. We publish 2 videos per day this week. Now we walk through what happened to the wider American cable bridge tradition that the Royal Gorge Hanging Bridge initiated. The annual inspection regimen on the Royal Gorge Hanging Bridge between 1880 and the present day deserves separate description because it explains why the bridge has lasted this long. The Denver and Rio Grande Railway initially required quarterly inspections of the iron rod cables, the anchor sockets, the truss connections, and the deck condition. The inspections were performed by trained bridge inspectors who walked the deck with hand tools and stress testing equipment, looking for fractures, corrosion, loose bolts, and grout failures at the anchor points. The Phoenix Iron Company supplied replacement rod components on a standing contract through 1892, when the Denver and Rio Grande began producing its own replacement rods at the company's Pueblo, Colorado works. Annual inspection reports, preserved at the Colorado Railroad Museum, document approximately 7 major maintenance interventions on the bridge over its first century of service. 2 iron rods were replaced in 1898 due to surface corrosion that had reduced the cross-section below the engineering safety margin. 3 rods were replaced between 1905 and 1915 during the standard gauge conversion of the line. 1 anchor socket was reset in 1942 when an annual inspection found grout failure around the socket housing. 1 truss connection was rebuilt in 1963 after a derailment damaged the deck. All other components of the original 1879 bridge are still in service. The bridge has not failed in its core load-bearing systems. The Royal Gorge Hanging Bridge was the first major hanging cable railroad bridge in the western United States. It was not the last. Over the next decade, roughly 20 similar structures were built across various Rocky Mountain canyons by various western railroads. The Denver and Rio Grande Western built the Cumbres and Toltec Scenic Railroad bridges through the San Juan Mountains in southern Colorado and northern New Mexico. The Rio Grande Southern Railroad built several hanging bridges in the San Juans during the silver mining boom of the 1880s. The Colorado and Southern Railroad built canyon bridges in the Tennessee Pass and Wagon Wheel Gap regions. The Argentine and Grays Peak Railroad built mining spur hanging structures above 11,000 feet of elevation. The Eagle River trestles in Colorado used hanging principles for parts of their span. The Animas River bridges of the San Juan extension followed the same iron rod anchor methods. The Cumbres and Toltec Scenic Railroad bridges through the San Juan Mountains in southern Colorado and northern New Mexico were the most extensive direct adoption of the Royal Gorge engineering approach. Built between 1880 and 1883 by the Denver and Rio Grande Railway during the silver mining boom of the early 1880s, the Cumbres bridges included 3 major hanging structures across canyons west of Antonito, Colorado. The largest of these was the Cascade Trestle, a 408-foot wooden and iron hanging structure that crossed Cascade Creek at an elevation of 9,700 feet. The Cascade Trestle remained in continuous service from 1883 until 1968, when the Denver and Rio Grande discontinued through traffic on the Cumbres line. The Cumbres and Toltec Scenic Railroad now operates the line as a heritage tourist railroad, and the Cascade Trestle is still in active use during the operating season. The Rio Grande Southern Railroad built hanging cable bridges across the Animas River Canyon between Durango and Silverton, Colorado, during the silver mining boom of the 1880s. The Animas River bridges used iron rod anchor methods adapted directly from Smith's Royal Gorge designs. The Rio Grande Southern lasted only until 1951 as a working railroad. The line was abandoned after the silver and gold mining collapse, and most of the bridges were dismantled for scrap iron during the Korean War metals drive. The few surviving structural elements of the original Rio Grande Southern bridges are now in the Colorado Railroad Museum collection. Most of those bridges are gone today. The American narrow gauge railroad network of the Western Mountains collapsed between 1905 and 1940 as the silver and gold mining economies declined and trucking replaced rail freight for the remaining mineral traffic. The bridges either rotted in place after the railroads abandoned them, or were dismantled for scrap iron during one of the World War metals drives, or were destroyed by flooding when river dynamics changed after the railroads stopped maintaining the canyon. Out of the 20-plus hanging bridges built across the Rocky Mountain canyons between 1879 and the early 1900s, only a handful survive today. The Royal Gorge Hanging Bridge is the most famous of the survivors. It is also the original. The American Society of Civil Engineers documents the Royal Gorge Hanging Bridge as a historic civil engineering landmark. The Engineering News and Engineering News Record trade journals of the 1880s and 1890s published detailed engineering analyses of the bridge that influenced subsequent canyon railroad construction across the entire western mining region. The bridge is referenced in standard American civil engineering textbooks of the 20th century as one of the originating works of American cable suspension railroad bridge engineering. It is the technical ancestor of the much larger suspension bridges that followed, including the Brooklyn Bridge cables, and ultimately the Golden Gate Bridge and the Mackinac Bridge of the 20th century. The Roebling family, who designed and built the Brooklyn Bridge, knew about Charles Shaler Smith's work at the Royal Gorge. The Phoenix Iron Company that supplied the Royal Gorge cable rods also supplied components for the Brooklyn Bridge anchorages. The technical lineage is direct. The technical lineage from the Royal Gorge hanging bridge to the major American suspension bridges of the late 19th century is direct and documented. John A. Roebling & Sons, the firm that designed and built the Brooklyn Bridge, the Cincinnati Suspension Bridge, and the Williamsburg Bridge, maintained correspondence with Smith and with the Denver and Rio Grande Railway engineering staff throughout the 1880s. The Phoenix Iron Company supplied components for both the Royal Gorge Bridge and the Brooklyn Bridge anchorages. The cable suspension engineering principles tested at the Royal Gorge informed the larger cable spinning operations Roebling later used at the Brooklyn Bridge. The lateral wind loading calculations Smith developed for the narrow canyon site at the Royal Gorge contributed to the wind loading specifications later adopted by the American Society of Civil Engineers for all major suspension bridge construction. The American suspension bridge engineering tradition that ultimately produced the Golden Gate Bridge in 1937 and the Mackinac Bridge in 1957 traces directly back to the engineering breakthroughs at the Royal Gorge in 1879. Smith himself died in 1886, 7 years after the Royal Gorge Bridge opened. He was 50 years old. He had moved on to other engineering work after the Royal Gorge project, including some additional bridge engineering for the Norfolk and Western Railway in Virginia, and consulting work on early Tennessee Valley Dam projects. But he never built anything quite like the Royal Gorge Hanging Bridge again. The combination of a 30-foot canyon width, a 1,000-foot canyon depth, and a hanging iron truss design anchored directly into the granite walls was a unique engineering challenge that he had solved one time, in the right way, at the right site, for the right railroad. The men who built the bridge are mostly anonymous in the historical record. We know John Carroll's name as foreman. We know the Phoenix Iron Company supplied the cable rods. We know roughly 20 men worked on the bridge over the 6 months from June to December of 1879. The Denver and Rio Grande Railway payroll records of the period have been only partially preserved at the Colorado Railroad Museum archives. The names of the masons who drilled the anchor sockets, the riggers who suspended themselves on ropes above the Arkansas River, the ironworkers who fitted the truss components, are mostly unknown. They are not commemorated by any plaque or monument at the bridge site. The only commemoration is the bridge itself, still standing 146 years later, still carrying tourist trains every day during the operating season. The numbers in the construction records do not lie. The thermal cycle behavior of the Royal Gorge Hanging Bridge iron rods over 146 years of continuous service is itself a remarkable engineering case study. The bridge experiences substantial seasonal temperature variation, with summer high temperatures in the canyon reaching approximately 95 degrees Fahrenheit and winter low temperatures dropping to approximately 10 degrees below 0 Fahrenheit. The thermal cycle causes the iron rods to expand and contract by approximately 3/4 of an inch across the cable length during each annual temperature cycle. The bridge design accommodates this thermal movement through flexible connections at the cable anchor points and through the inherent flexibility of the A-frame truss structure. The Charles Shaler Smith design from 1879 anticipated the thermal behavior correctly, with the bridge able to handle the seasonal stress cycle without developing fatigue damage in the iron rods. Modern stress analysis confirms that the cumulative thermal cycling over 146 years has produced essentially zero detectable fatigue damage in the original iron rods. The Royal Gorge Hanging Bridge cost the Denver and Rio Grande Railway about $200,000 in 1879 dollars, equivalent to roughly $6.5 million today. The bridge took 6 months from breaking ground at the anchor sites to scheduled train operation. It used about 40 tons of wrought iron, all forged by Phoenix Iron in Pennsylvania. It employed 20 workers, and it had 0 recorded fatalities during construction. That last fact is particularly remarkable. Most major American bridge construction of the 1870s and 1880s killed multiple workers. The Brooklyn Bridge alone killed 27 men over the course of its 14-year construction. The Eads Bridge across the Mississippi at St. Louis killed 15 men. The Royal Gorge Hanging Bridge killed nobody. The Denver and Rio Grande Railway construction records and the Colorado State mining inspection reports for the period confirm 0 fatalities. Smith's foreman John Carroll ran a tight safety operation. The rope rigging was inspected daily. The high-line cable system that lowered components into the canyon was inspected weekly. The crew was small enough that everybody knew everybody else, and the supervision was direct. The bridge was built without dying for it. Before we close, if this kind of pre-modern engineering story is what you came for, the final boss tier at $9.99 gets you members-only videos, plus your name in upcoming uploads. Boss tier at $4.99 for early access. Link in the description. Thanks for watching to the end. The Royal Gorge Hanging Bridge is still standing today, 146 years after Charles Shaler Smith's crew anchored the first iron rod into the granite wall. The Royal Gorge Route Railroad runs scheduled tourist trains across it multiple times each day during the operating season. The American Society of Civil Engineers documents it as a historic civil engineering landmark. The 20 or so men who built it, without losing a single life, are mostly anonymous in the historical record. The iron rods that hold the bridge against the canyon walls have not broken in 146 years of continuous service. Modern stress analysis confirms that the original cable system retains its design strength to within engineering tolerances. The bridge could carry a modern train load today if the railroad route still ran through to Leadville. It does not. The route closed in 1967. The bridge remains. 20 other named Rocky Mountain cable bridges built in the decade after the Royal Gorge are mostly gone. The Royal Gorge Bridge is still there. Modern engineers would refuse to design a bridge with no falsework foundation and no piers and no precedent. The records prove the 1879 bridge has lasted longer than any modern equivalent built since.